Hello everyone. In this video we will talk about partial derivatives, which are an analog to the normal derivative you're used to from single variable calculus, as well as the analog to the tangent line, which is the tangent plane. Alright, so first let's recall the definition of the derivative in single variable calculus, right? So we had this limit definition of the derivative, and basically we were looking at the limits of the slopes of secant lines, right? And then, at our x naught, we would actually get this tangent line, and this was the slope, right? And so we would like some sort of analog in multivariable calculus. But the issue is, right, in one variable, you only have one direction to talk about, right? You're talking about like how your x changes, and then there's a corresponding effect on y. Here, if I talk about like the top point on this, kind of overturned bowl shape, well, how do I talk about a tangent line, right? I can go in all sorts of directions, right? I can go in basically any direction in 360 degrees from this point. And so how do I talk about this? Well, the idea is to bring it down to one variable by fixing either x or y. And so this leads to a notion of a partial derivative. Okay, so it's basically either going to be you fix x and look at a change in y, or you fix y and look at a change in x. And so let's go ahead and look at the formal definitions. They're going to look very familiar. All right, so here is the partial derivative of f with respect to x. So notice I just put like a little subscript x down here, f sub x at x naught, y naught. So I should be specific here, at x naught, y naught. And so what we do is basically the same thing that we did in single variable, except for, like I said, we're holding y constant here. So by holding y constant, I mean that there is no change. So it just sticks, right? I start at my point x naught, y naught. And then as I'm changing direction, I am only moving in the x direction, right? This h only affects my x coordinate. My y coordinate is fixed. And so, if you look at this picture, right, we're either moving left or right on the x-axis, and so that would be like traveling down or up on this bowl shape from our point, because we're only moving in the x direction. And as you might suspect, the definition for y is very similar. So here, right, we do f sub y, and we are only taking a small change in our y coordinate and looking at the corresponding change. So we're only looking at the slope in the y direction here, and this would mean we're going kind of around our bowl shape instead. So you're really just fixing one of the directions, and so this ends up looking almost kind of like a cross thing where one of them is only moving the x and one is only moving in the y. So there is a lot of notation here just to get used to. So you'll see sometimes the partial as f sub x, or, if it's z equals f of y, you may see z sub x, or f sub x without the coordinates put in necessarily. If you're just talking about the function, you may also see the del f over del x. We had the similar notation with like the df dx in single variable. This is kind of the same thing, but we use this del for partials. And so you'd have similar things for y. Just replace every instance of x with y there. So now let's go ahead and look at how to actually compute these things. So we'll look at our favorite, again, bowl shape, this paraboloid, x squared plus y squared. So, you don't have to use this whole limit definition here. We can really use the fact of what I said. You should treat y as a constant when dealing with the partial with respect to x. You're only thinking of the change with regards to that one variable. And so if y is a constant, right, if you saw, for instance, x squared plus 5, you would say its derivative is 2x, right? Well, y squared is just a constant, so treat it like 5 here. This is just going to be 2x. And then similarly, when you take the derivative with respect to y, you're going to get 2y because you are holding x constant, okay? Okay, what about this one? Well, turns out chain and product rule still work. Okay, so those still make sense, but again, you just have to think one of these is being held constant. So here I'll write another notation, so we'll do del g del x. Here is going to be, well, chain rule. So cosine goes to negative sign, still do the inside, but here y is constant, and so the derivative of xy is going to be y, right? Because again, y is constant, x is my variable. And similarly, this one is symmetric, right? So this is going to be the same, just replace that y with x, because the derivative of xy with respect to y would be the constant x. Okay? So let's try one that's not symmetric, for instance. So this one, I actually have 3 variables, so this would be in like 4-dimensional space, so we're not going to try to draw this or anything, but we have 3 partials to talk about. So del f, so the partial with respect to x. Now y and z are constant. Okay, so we have to think about each term. Okay, so cosine of z is just a number, so this becomes cosine of z, plus, again, this stuff is all constant, so you get plus 2y cubed e to the z x. This whole guy is a constant. Okay, with respect to y, well, your first term is just a constant, so that goes to 0. And then the second one, you've got 3y squared times your constant x squared e to the z. And then finally, with respect to z, cosine of z becomes negative sine z, so negative x sine z, plus, well, e to the z just stays at e to the z, and the constant hangs around out front. So that doesn't really change, okay? All right, and so for your first exercise, I just want you to find both partials for these 2 functions, and so neither of these are quite symmetric, so they're at least a little bit interesting. So something that we'll need for later is the notion of a second partial. So just like in single variable, we have second derivatives, but here, right, we're talking about partial derivatives, and so we actually get this branching of like we have 4 second partials, 8 third partials. You keep multiplying by 2 because you can do it with either variable after doing the first one, right? So you can do it with respect to x and then x again, or with respect to y. So let's just see an example. So the first thing we want to do here is just find the actual first partials. So fx, well, we get 20xy cubed plus 2x. The other 2 are constants, so go to 0. Fy, we get 30x squared y squared. Next is a constant. Next one we get minus 2e to the 2y, and then another constant, so those are 0. And then fxx, we just do this with respect to x again. And by the way, notice on the notation here that these go left to right, but then the del notation works like right to left because function composition works right to left. So notice up here that we have like xy, but then this goes back as xy, so it looks like yx. Just something to point out. So this one, we're going to get 20y cubed plus 2. Fyy is going to be 60x squared y minus 4e to the 2y. And then the interesting ones is to look at the mixed partials. So f of xy means we start with this f sub x here and then do it with respect to y. So we're going to get 60xy squared, and then 2x is constant. Fyx, we start up here with fy, and then we are going to get also 60xy squared. And this is no accident. In fact, so long as you have nice functions, these are always going to be equal and the order will not matter. And so for your second exercise, I just want you to find the 4 partial derivatives for this multivariable function. All right, so the last thing we want to talk about is linear approximation. So in single variable calculus, we had a point x naught, y naught, and we could find a line that was accurate, really close to a point on your graph by finding the tangent line, right? And so we can do the same thing here, except for we can go in any direction, right? We have a whole bunch of tangent lines. And so we actually don't end up with a line. We end up with a tangent plane, which allows you to go in all of these directions that are tangent. So we actually get the tangent plane. So now the question is, how do we actually get an equation for such a thing? So what defines the tangent line to be the linear approximation is these 3 things. 1, it's linear, so it puts the linear in linear approximation. And then it's actually equal at the point, right? And then the line also has the same slope as the slope at that point on your graph. So we want to find the same thing in 3 dimensions. So first, L of xy should be linear, right? So this is now 2 variables. And by linear, we mean the following. So it has this kind of equation, and no, this isn't a line. Again, this is a plane, but it's called linear because you're only seeing first powers of x and y. And then we also, again, want it to agree at the point we care about, and then have the same, instead of slope, the same slopes in the x and y direction. Okay, so let's take our classic paraboloid here at the point 2, 1. So we know that L of xy has to be in this form. And so L of 2, 1 is going to be, well, you plug in these, they're both 0. This gives you C. Lx of 2, 1, well, the only x thing showing up is ax, so this is A, and Ly of 2, 1 is B for the same reason. And so you would have to look at, okay, what happens here? So f of 2, 1 is 5. Fx of 2, 1, we already saw fx is 2x, so this is 4, and fy is 2y, and so this is 2. And so this tells you immediately that C must be 5, C must be 5, A must be 4, and B must be 2. And so once you have that, you have exactly your tangent plane to this graph at the point 2, 1. All right, thank you for watching.